Hi, this is Mrs. Cribb, and I'm going to do a freezing point depression example problem for you. I went ahead and wrote the the mole freezing point constant up here that we're going to need. Now, let's read the question. A solution contains 55 grams of methanol. This is the formula of methanol. It looks like this. It has 3 hydrogens around it, and then one OH group. That OH group is different. This makes this polar, and this side is going to be the negative side, so if you had to draw the dipole moment, you'd point towards the OH group. It's dissolved in water, and remember water is also polar, H2O, so we have 2 H's and an oxygen, and this side is negative and this side is positive. So a polar solvent will dissolve a polar solute. Another solution contains 65 grams of methanol and 475 grams of water. We're going to calculate the molality of each solution. So first of all, even though I just mentioned which is which, you always have to determine which one is the solute and which one is the solvent. So we have 2 solutions, okay? And in the solution number 1, we have 55 grams of methanol and 250 grams of water. Well, whatever you have more of, that is the solvent. So here, the solvent is water, and then the solute is the methanol, because we have less of it. Now, in the second solution, it's the same thing. We have more water, making it the solvent, and less methanol. It makes it the solute. Now, well, the solute is, we have to determine, is it ionic or covalent? Okay? In this case, this one is covalent, because carbon is a nonmetal, hydrogen is a nonmetal, and oxygen is a nonmetal. So we have all nonmetals. And when we have all nonmetals, we have a covalent molecule. And that means that our I value is going to be just a 1. Okay, now if it was ionic, like sodium chloride, that's ionic because we have a metal and a nonmetal. The I value would be 1, 2, 2, because there are 2 atoms, 2 ions. But we don't have that in this case. We just have a covalent molecule. Because the water is the solvent, once we determine the solvent, the molal constants, whether it's freezing or boiling, come from the solvents. And so that's why I wrote it up here already for you. So in this case, we look it up on a chart and we find it's 1.86 degrees Celsius per molal. So what I really want you to notice is this. The solute determines the I value. The solvent determines the constant value. All right? So, and remember that you have to determine if the solute is ionic or covalent. So there's the first thing you do. Which one's the solute? Which one's the solvent? Is the solute ionic or covalent? If it's ionic, count the ions. If it's covalent, the I is 1. With the solvent, once you know what it is, you can just look up either the freezing point constant or the boiling point constant off the chart. Now, since we have 2 solutions, we're going to have to do 2 calculations. We're dealing with freezing point, so it's delta T sub F. Whoops, there we go. Delta T sub F equals a negative I K sub F M. That's how I have it written on your reference chart. The other way is to put the negative sign on the other side. So I'm going to write this twice. Delta T sub F equals a negative I K sub F M. Remember that the I values are particle counts. Okay, the I values are particles, the number of particles. That's what the I values are. The KFs are the constants, and little m is for molality. Okay. For solution number 1, we have 55 grams of methanol and 250 grams of water. So the I value is negative 1, or 1, and it's just the negative sign in front of it. So it's a negative 1. The KF is 1.86 degrees Celsius per molal. I don't know the molality though. On the second one, I have the same thing. I have a negative 1. I have 1.86 degrees Celsius per molal, but I don't know the molality. So I need to calculate the molality of solution 1. I'm going to kind of divide a line down here. All right, for the first one, we have 55 grams of methanol. So molality remember, is going to be moles of solute over kilograms of solvent. All right. I don't have the moles of solute. I am able to figure out the kilograms of solvent. So I'm going to erase these things real quick just so that I can talk about it. With the solvent, we already determined is water. Right there. That's the solvent. And so I need kilograms of solvent. And so I just need to divide 250 grams by 1,000 because there are 1,000 grams in a kilogram. See, 250 grams. There are 1,000 grams in a kilogram. So I just divide by 1,000. I end up with 0.250 kilograms. I have to keep all three significant figures. So for the first one, 0.250 goes on the bottom. Yeah, I'll get that out of the way after all. 0.250 kilograms goes on the bottom. And then for the second one, let's calculate the molality of the second one. The moles over the kilograms on the second one. The kilograms for the second solution, I have 475 grams. So divide by 1,000 again. 1, 2, 3. I have 0.475 kilograms. Okay, so I got the solvent kilograms on the bottom. I have to figure out the moles of both. So let's look at the first one. I have 55 grams of methanol, which is CH3OH. I don't have the moles, so I need to calculate the moles. So 1 mole of this, and I got to know the molar mass. So let's calculate the molar mass. We have 1 carbon, and we have hydrogen, and we have oxygen. We have 1 carbon, but we have 4 hydrogens, and make sure you look at that. We have 3 of them right here, and 1 more right over here. So 4 hydrogens, and only 1 oxygen. Carbon is 12.01. Hydrogen is 1.01, and oxygen is 16. So let's pull up our calculator and go ahead and calculate the molar mass of methanol. So 12.01 plus 4 times 1.01, so 16.05 plus 16 is 32.05 grams per mole. That's the molar mass of methanol. So I can use that here. Sorry, 32.05 grams. And the moles on top. So now I'll pull up my calculator and calculate the actual number of moles. 55 divided by 32.05. And I get 1.72. I need 3 significant figures, 1, 2, 3. So 1.72. I got to round the 1 up to a 2. 1.72 moles. So I put that here. 1.72 moles. And now I can put that in my calculator and calculate the molality. 1.72 divided by 0.25, 6.88. 6.88 molal. That's the molality of the first one. That's the calculating the molality of the first solution. So that's answer number 1. Now I need the second one. I already got the molar mass, so it would be easier. In the second one I have 65 grams. So let's say 65 grams. 1 mole is 32.05 grams. And I put that in my calculator. I get 65 divided by 32.05, and that is 2.03. Again, I need 3 sig figs, 2, 0, and then the 2 has to be rounded up to a 3. 2.03. 2.03 moles. So now 2.03 moles up here, and that I can calculate the molality. 2.03 divided by 0.475 gives me 4.27. 4.27. 4.27 molal. All right, that's the molality of the second solution. So now I can just put those molalities in. So the first one is 6.88, and the second one is 4.27. Notice that I can cancel out the molal units. and I will have a negative temperature on both sides because we're talking about the change in the freezing point right now, the change in the freezing point. So let's calculate that one for both. Now you can do it without even doing the math. You should be able to see that I'm multiplying by a larger number on this side, so this one's going to be a lower negative than I am going to get from the other side. And that's part of the logic of being able to just calculate which one's going to be affected the most. Okay, so now we have 1.86 times 6.88, and it's 12.7968. I need three significant figures, so 12.8. A negative 12.8 degrees Celsius on this side, and on the other side, 1.86 times 4.27, and that gives me a negative 7.94. Now, this could have been different if we were dealing with ionic molecules and these I values were not ones, but in this case they were ones. So we can see that the first solution, the boiling point is going to go down by, the freezing point is going to go down by 12.8 degrees, and the other one is going to go down by 7.94 degrees. So calculate the freezing point though of each solution. Now this looks like it is the freezing point, and it will be in this case because water's freezing point is normally 0, but if you didn't have water as a solvent, you would have to do another calculation. So we're going to pretend that we don't know that this is going to be the answer. So next thing we need to do is write the second formula, and it's the new one minus the original one. And we're going to calculate the new freezing point. So what it's really asking for is this. It's asking for the freezing point of the solution. Remember, the T sub n is for the solution. It's the freezing point or the boiling point of the solution. The T sub O is the freezing point or the boiling point of the solvent, the pure solvent with nothing in it. All right, now we just calculated the delta T sub F right here. So we're going to use it. Negative 12.8 degrees Celsius equals T sub n, which is the freezing point of the solution, minus the freezing point of the pure solvent. Well, in this case, the freezing point of the pure solvent is 0 degrees Celsius because we're dealing with water. So we just, nothing to add. So that means that we add 0 to both sides so that the new freezing point is a negative 12.8 degrees Celsius. And that seems like silly. You notice they're equal to each other. They're only equal because the original freezing point is 0. If you look on your reference charts, you can see freezing points of other molecules, other solvents that are not 0, so you would actually have to add values on here. And for the second one, we could do the same kind of thing. The delta T sub F is actually this value right here. So negative 7.94 degrees Celsius is T sub n minus 0 degrees Celsius, so that the new freezing point is a negative 7.94 degrees Celsius. Okay, this seems like a lot of work, but it's really not difficult work, and we actually did two problems. We calculated the freezing point of the first solution and the freezing point of the second solution, and you can see that the first solution, because the molality was higher, that means the concentration was higher, the freezing point went much lower than the second solution. So the higher the molality, the lower the freezing point will be if you're dealing with the same kind of solvent like water and the same kind of solute. Okay, I hope that helps, and I'll see you soon.